This is MV Ramanna. As part of UN Austria Post-Symposium tutorial on Earth Observation for Climate Action, I'm going to introduce basic concepts of climate change. Before we go on to the climate change, let me introduce what is the Earth's climate system to begin with. The Earth's climate system encompasses atmosphere, hydrosphere, cryosphere, biosphere, and lithosphere. Atmosphere is nothing but the envelope around the Earth's surface, that is all the atmospheric composition, whether it is clouds or it is water vapor content and all the greenhouse gases, aerosol, suspended particulate matter and everything. And hydrosphere consists of oceans, rivers, lakes, all put together we call it as hydrosphere. And the cryosphere is sea ice sheets and glaciers, all the ice mass related things and all comes under cryosphere. And the biosphere is all the vegetation and then all the things. And then the lithosphere is the topmost layer of the Earth's surface. And all these things interact at different time scales, but the main source of energy is sun's energy is the main driving force. All these things, the interactions and everything takes place mainly because of the solar energy input. Now, once we understand the climate system, and then what are the things that are causing changes to the climate system? Basically, sun is the since the sun is the main source of energy, so any change in the sun's input energy itself can alter the earth system. So first is sun's strength, and then the sun earth distance related things like eccentricity of the earth can change, and also the inclination angle and precision. All those things comes under this earth's orbit around the sun. The third thing is earth itself, the plate tectonics movement and all also can change the landmass, the distribution on the earth's surface, ocean landmass distribution. And the more another important thing is volcanic eruptions, which is also as part of the plate tectonic movements. All these things can change the Earth's climate system. That is what I have given the left-hand side, all these changes. And the middle is the climate system, that is what all the five components. And the right-hand side is the variations or the changes that you see. As the input changes, you see the changes in the output. On top of these things, and the human beings are also changing the Earth's atmosphere system in the way adding more gases to the atmosphere, polluting the planet, and also changing the land surface. All those things human beings are also contributing. But these changes are happening at different time scales. For example, all these plate tectonics are the slowly moving changes, and you see the changes of the order of million years. And also this Earth's orbit is also the changes in the eccentricity and all takes place around 100,000 years. And also the inclination angle also changes of the order of 50,000 years. These are all slowly moving, but the cycles are of the order of anything above 50,000 years or so. But the human changes are happening that are lower time scales, and those changes are which are basically driving the changes in the Earth atmosphere system. That is what basically I'm going to discuss now, how the human beings are contributing to the change, contributing to the changes in the Earth's climate system. And to begin with, to understand the changes are happening and all, we need to understand the planet Earth's temperature itself. How do we calculate, first of all, to begin with, its planet temperature? It is simply basically, as I said, sun is the main source of energy. Whatever the energy comes in, it should be balanced by what goes out. So simple equation, the balance equation, what comes in is S naught is solar constant, and then by 4 is like diurnal, and then globally if you average, you get close to 1372 is the solar constant, it becomes 342. That's why it becomes S naught by 4. And alpha is the reflectivity. Anything falls on that surface, some amount get reflected back, and the top of the atmosphere, that is what you see 1 minus alpha into S naught by 4, which should be balanced by the emission from the Earth's surface, that is sigma t to the power 4, that is Stephen's Boltzmann's law. So if you do those simple arithmetics, you get Earth's temperature is close to minus 18 degrees centigrade. But if you introduce the Earth's atmosphere and also introduce the basic physics like atmospheric window and other physics interactions and all those things, if you introduce, and then if you do the similar balancing, what comes in and what goes out, if you balance out, you get the its temperature is close to 15 degrees centigrade. That is what we are seeing now. Our Earth's temperature is very close to on a global mean. All the planet Earth's temperature altogether, if you take the average, it comes to anywhere between plus 10 or around plus 15 degrees centigrade. So what this atmosphere basically is causing, the temperature of the Earth goes from minus 18 to plus 15 degrees centigrade. That is close to plus 33 degrees centigrade. So who is causing this plus 33? If you do further radiative transfer calculations, out of 33 degrees plus 33, 21 degrees warming is coming from the water vapor itself, and 7 degrees is coming from carbon dioxide, and 5 degrees is coming from other gases. So all these put together, they are actually helping the planet to be at a livable condition, like a warm planet of the order of plus 15 degrees centigrade. So those gases, these gases which are causing planet to be at a warmer level, we call them as greenhouse gases. These greenhouse gases are contributing to the greenhouse effect. That greenhouse effect is causing planet to be at a livable condition. But now how this process, what is this greenhouse effect, how it is happening? To explain this, so what is the basically, before I go in explaining the greenhouse effect, let us try to understand atmospheric composition itself. If you take 1 million molecules in air and you take it to the lab and we do the chemical experiments, and we get to know almost 78% consists of N2 molecules and 21% consists of oxygen molecules, and around 3900 is water vapor molecules, and 280 molecules is carbon dioxide, and almost less than 1 molecule is methane. So that 280 is what we call it as ppm, means if you take 1 million molecules, out of which you are getting only 280 CO2, that's why we call it as parts per million. That's how we use the word ppm. So 280 ppm is the carbon dioxide. This is what the planet we got initially. The red colored ones are the ones which are contributing to the warming, that is plus 33 degrees centigrade, means minus 18, it is taking to the plus 15 degrees centigrade. But now if you see the current condition, the water vapor molecules have gone up by 210, but these are all variable gas, because it varies time to time depending upon the convective activity and the transport, and then the rainfall. All these things causes change as variable, but put together around 210 molecules have gone up in the atmosphere since 1750. But if you take carbon dioxide, it's almost gone up by 50%. Now it is close to anywhere between 420 ppm, the CO2 levels in the atmosphere, and then methane has gone up by 1 molecule. The reason why we are comparing 1750 is that is a time where industrialization has started. That is where the James Watt has invented the steam engine. Since then we started using the fossil fuels. That's the reason why the composition, this carbon dioxide molecules and methanes and all these things have gone in the atmosphere. You try to understand now, since the CO2 and H2O and CH4 alone has caused around 33 degrees warming, that is initially to begin with our planet. With this increase in the greenhouse gases, we should expect more warming. And this warming is what is causing the climate change now. Why only these gases are called, we call greenhouse gases? Because as you might have learned in the quantum physics, we know that only water vapor, carbon dioxide, and methane and nitrous oxide, they undergo vibrational and rotational mechanisms through which they absorb infrared radiation at particular wavelengths and they emit back. Because of those processes, our Earth's atmosphere is getting added up more um, as Earth emits radiation. These gases are absorbing, not allowing this radiation to go back to the top of the atmosphere, and they're retaining it and they're causing the more warming. So these gases are called greenhouse gases. The warming that they are contributing, the mechanism is called greenhouse effect. The greenhouse effect accumulation is causing the warming that is what we call as global warming, and the global warming contributes to the climate change. As I said, let us look into the what is the greenhouse effect. The greenhouse effect is to explain it in a simplistic way. As I said, sun is the main source of energy. This thin, the white line is the, let us assume there is a blanket, that is the atmospheric blanket above that surface. The the Earth atmosphere allows sun's radiation to pass through that and it reaches the Earth's surface, and Earth absorbs this radiation and it emits. Anybody above 0 degrees Kelvin emits radiation as it is emitting in the red lines. Whereas if you see, very less amount is only coming back to the Earth and majority is going getting back to the top of the atmosphere. But if we thicken the blanket, what is happening? It is trapping more radiation, what is coming from the Earth's surface, and it is adding it to the Earth's temperature and is causing the Earth's temperature to go up. So this is how this greenhouse effect is being enhanced by this atmospheric composition or greenhouse gases. That is what I'm trying to say, that the gases which are contributing to this greenhouse effect are called greenhouse gases. The greenhouse effect causes causing the enhanced greenhouse effect is causing the global warming. That global warming accumulation over the period of time is causing climate change. But if you see, this concept is not new. It is known somewhere else. 1820 onwards, scientists start working on this. If you see in Fourier, 1820 itself, he described how the planet atmosphere is, contributing to warming the Earth's surface, and followed by John Tyndall. He invented the sensors to measure all these gases in the lab. Through that, he found that CO2 is the major contributor in warming the planet. But later, a significant study has come from Arrhenius, who showed, doubling the atmosphere, how much really the Earth's temperature goes up. That was still we consider that is the basic paper, and he has done it in 1850. He showed around 4 degrees warming takes place or by doubling the atmospheric CO2 levels. And then there was some work was going on in around 19th century. It's around 1900. Bands, absorption bands get saturated, especially in the presence of water vapor. So there was some debate was going on at that time. And then once again, Arrhenius, and then he kind of refuted the Angstrom hypothesis and said the H2O and CO2 bands are different. And then H2O does warming as well as CO2 also warms the planet, but they are distributed vertically at different locations. So he kind of um, um, did a lot of calculations and showed by doubling of CO2 can cause around 4 degrees warming in that temperature. So this is the kind of history back in time, and this is how these greenhouse gases were invented, and in the laboratory studies on how they're contributing to the greenhouse effect, and then in turn contributing to the global warming and climate change and all. When these things are going on, the satellite observations have really revolutionized how to really quantify these energy flows within the Earth's atmosphere system. And then to begin with, in around the 60s or 70s, where the remote sensing sensors started start providing the data on the different parts of the climate system. Whereas around 80s, we started, getting the radiation measurements, kind of Earth radiation measurement, RB satellite, followed by Ceres satellite, and then followed by our Scarab onboard megatropic satellites. They all have provided the energy distribution or the energy flows within the Earth atmosphere system. If you see, the left-hand side is mostly dominated by short wave. That is what we get from the sun's energy. And then the right-hand side is what Earth emit and how it reaches back to the top of the atmosphere. I would like to draw your attention here that Earth emits around 390 watts per meter square. And if you see on the top of the atmosphere, it is around 235. See, as Earth is emitting, even though Earth is emitting 390, by the time it reaches top of the atmosphere, it is only 235. The difference between these two is close to 155 watts per meter square. That is what is being, atmosphere is trapping this 155 watts per meter square, and this is what is causing our planet to be at a livable condition. That is what we learned at plus 15 degrees centigrade. But over the period of time, we have added greenhouse gases, we have thickened the blanket, and that alone is contributing to 2.7 watts per meter square. So the satellite data, especially Earth radiation budget data, when started providing, that is the era, we call it as golden era of satellite observation, since it is able to provide the details about energy flows and also helping us to link the relationship between greenhouse gases and how they are contributing to the warming the planet, and also able to understand the feedback mechanisms within the Earth atmosphere system. And then not only that, it has also helped us in precisely quantifying how each gas contributes to the warming the planet. If you see, for example, carbon dioxide, it is warming around 2.16, means around close to 2 watts per meter square. The surface, it is warming around 2 degrees. Whereas if you put together methane, nitrous oxide, and halogens, if you put together, they are all contributing close to 1 degree. And similarly, surface level ozone is contributing to around zero point 0.5 degrees centigrade. And similarly, water vapor and all. Whereas the land cover changes are observed to be, cooling the planet by around zero point 0.2 degrees. Whereas the black material that deposits on the snow and ice, anything of the black nature, it absorbs the radiation. Anything in white generally reflects back. So this absorbed energy is further adding and melting the snow and ice. That process is contributing to the warming around zero point 0.8 watts per meter square. And then our own aviation industry, the effluents that comes from the aviation industry, all those gases alone are contributing to around zero point 0.06. On the other hand, aerosols, there are tiny particles in the atmosphere. They scatter the radiation back to the top of the atmosphere, and also they act as a cloud condensation nuclei, and they influence the cloud formation. That aerosol and cloud interaction, and then the cloud lifetime effect, all those things, and also aerosol radiation means they scatter the radiation back to the top of the atmosphere. All these processes observed to be cooling the planet Earth, so that they are of the order of -1 watt per meter square at the surface. If you add all those things, it is coming to 2.72. This is what I have shown in the previous slide, that around 2.7 is what we have added to the planet Earth. And then these are all in watts per meter square. If we wanted to convert this into degree centigrade, we need to know the climate sensitivity parameter, which depends upon these feedback mechanisms, that ocean atmosphere, land and ice, and all these feedbacks that goes within that atmosphere. We need to know that sensitivity parameter. And this is why IPCC has, did a lot of research. The scientists who are involved in IPCC, and they were even given the Nobel Prize for finding that climate climate sensitivity parameter. If you use those parameters, that helps us to document, convert into how much it is coming to the warming the planet. See if CO2 is contributing to around 1 degree centigrade at the surface like that, all put together it is coming to close to 1.27 degrees. So it is very close to the number that what we are seeing now. It is close to 0.8, 0.9 degree. Observations are showing close to 1 degree, and remaining heat, some amount of heat is gone into the oceans. So these calculations and all are possible, and also we are able to link each and everything is because of the satellite data, availability of the Earth radiation budget satellite data, and simultaneously the availability of these gaseous measurements and then aerosols and then this um, data on glaciers melting and all. So we are able to precisely document the contributing agents to the warming. And then how do we relate it to the natural versus, as I showed in the previous, the second slide, that natural and then human being, that is what we call anthropogenic forces. If you incorporate all this satellite data and known physics in the model and we try to reproduce the temperatures, unless we incorporate anthropogenic forcings, we are not able to reproduce the observations. The black line here in the top figure shows the observations, and red line is the model. If you incorporate anthropogenic and natural, but if you incorporate only the natural, we are not able to reproduce the measurements. This clearly shows that the anthropogenic signal is what it is contributing to the recent changes. And not only that, if you do the similar work on land surface alone, this is once again observations and model, it is able to reproduce, models are able to reproduce the observations only if you incorporate the anthropogenic changes. It's same is the oceanic heat content, and this is there in IPCC 2018 report. That is where they said it is humans are the majorly contributing to the climate change or global warming. And also if you see the another important thing is sea level rise. If you see, we have observations from 1880 onwards, tide gauge observations, and then the satellite data, altimetry data is available from around 1980s onwards. That data also shows that there is a sea level is gradually increasing over the period of time. And who are all causing this increase? If you see, the major contribution is coming from thermal expansion of the water itself. As sea surface temperature goes up, it warms the water. It's because of that the thermal expansion takes place. Apart from that, the glaciers melted water is contributing to the sea level rise, as well as Greenland and then Antarctic melting. These are all contributing. So these are all once again coming from the satellite altimeter data and then sophisticated sensors recently that they have launched is able to provide continuous data which are able to help us to really see what is happening in the sea level. And similarly, if you come to the Arctic, this is the image, September 18, 2022 image. The white patch shows the presence, the Arctic presence of sea ice or Arctic in 2022. But if you see last 30 years mean picture, that is shown through yellow region. What is happening is Arctic sea ice extent is really shrinking, and it has a significant impact on the climate change. Basically, anything of the white in nature reflects back the incoming solar radiation back to the top of the atmosphere. Whereas the moment it becomes, water is a good absorber. It almost absorbs around 90% of the energy. Thereby, less amount energy goes back to the top of the atmosphere. This retained energy, which further warms the water and then it further melts the Arctic. So that is what we call it as a feedback mechanism. How do we know? These are all the satellite data, laser-based, microwave-based satellite data sets are nowadays are available, which shows how the volume of the Arctic sea ice extent is gradually decreased over the period of time from 2004 to 2020. And then on top of that, as I said, we have sophisticated radiation measurements which are able to basically we are able to really measure this albedo. Now it is over Arctic, the albedo has decreased by 0.04. That small 0.04 is contributing around 7 watts per meter square of warming. Means per each meter square of area over that region, there is additional energy of 7 watts is there. You can imagine how fast it may melt in the near future if you allow this thing to happen. So these are all the kind of things that we are seeing right now. What we are seeing is we have seen the unprecedentedly the CO2 levels are increasing. They are all highest as of now. Similarly, sea level rise, was I have shown you, there is increasing. Arctic sea ice level area is shrinking, and also glaciers are also shrinking. All these things are are happening. And then what happened is, while these observations are going on, um, um, the scientific community has decided to make the data sets available to the scientific community. In the process, committee CEOs, Committee on Earth Observation Satellites, have defined essential climate variables. In the atmosphere, they have some parameters, ocean and terrestrial part, and which includes the cryosphere also. They have defined these parameters. These parameters are very much important for us to see is there any changes happening, and also to understand the feedback mechanisms and all. So these are the list of essential climate variables. The data is very much needed for us to understand and also to quantify the changes as to meet that um, commitments. ISRO has come up with a program called a NICES program. NICES stands for National Information System for Climate and Environment Studies. There is a portal is created, and then using the available satellite, national as well as international satellites, we are retrieving and disseminating those parameters, and this data is freely available in the public domain. Anybody can access this data. Right now, they have defined, COS has defined around 55 essential climate variables, out of which around 28, 25 only can be retrieved using the satellite technology with the current existing technologies, and out of which around 13 are, in ISRO we have around 13 variables that are close to be called as essential climate variables. While um, uh, to meet this UOS, and we need the data sets, we need to understand, for us to understand this climate change, we need to have basic data sets. When this data sets preparation is going on in recent decade, this climate change has morphed into a kind of climate disruptions where it is causing a lot of climate crises, like we are observing extreme heat conditions we are seeing, and also we are seeing heavy rainfall and drought conditions. We are seeing fire events are happening, and ocean has become the more acidification, and there is a loss of oxygen. And then if more details, one can go through that bulletin of American Meteorological Society Journal in 2020. They have a big volume talking and explaining about this extreme weather events. These are all numbers I have taken from that report only. When these receptions are going on, and then how to mitigate, that is what the Paris Agreement is all about. Can we bring down the emissions to a level where we can keep the planet temperature at close to 1 degree, and also that is what the Paris Agreement is all about. And they suggested to, instead of using CO2 carbon dioxide, can we go and can we depend upon renewable energies, and as a other alternative source of energy, or geoengineering approaches are all discussed in limiting the climate change. And these are all the issues that I thought of sharing it with you, along with basics on the climate change. Where do we stand now is, now we started seeing the extreme weather events. Unless we control these greenhouse gases, these extreme weather events are going to become more intensified. And then to understand the future, we need to really understand what is the current stress levels of our climate system, and then we have to understand adaptation strategies. If you see these extreme events happens and simultaneously how to cope up with that. And then lastly, we need to integrate all the data sets that are coming from different platforms and see how we can address this risk assessment related studies. That's where I think the future research we have to focus upon. That is where our NICES program go ahead and is planning to address this risk assessment and climate resilient related studies. And thank you very much.